Hey everyone, in this lesson we are actually going to cover the last two functions that we need to take the derivatives of. We've covered every function that you can think of. There's only two left, and we're going to cover those in this lesson today. After this, we're going to transition to obviously practicing a lot of taking derivatives, but moving into the realm of applying the idea of the derivative to graphs, to life, to application-based problems. So we can't do that though until we finish this last lesson. Now remember, last time we talked about the derivative of e to the x and how that derivative is the same as the original function. The derivative of e to the x is e to the x. We also talked about the derivative of natural log of x being 1 over x. We're going to use those today to talk more broadly about all exponential functions and all logarithmic functions. So with that said, let's go ahead and take a look at those two functions. Like I said, there's two left. We've got exponential, which is, we'll refer to it as a to the x, where a is a constant, so it could be 3 to the x or 7 to the x or something like that. And then we have this other function, log base a of x. Again, a is a constant here and x is our variable. So with that said, let's go ahead and see if we can develop the derivative of any exponential function. So if we say let y equal a to the x, and I'll go through it with a parallel example with, let's say, 3 to the x, just so you can have a bearing, because I know the more letters we throw into things, the more confusing it can be. So first of all, I don't know how to take the derivative of that. Okay? I can't use the power rule because remember, the power rule is reserved for when the variable is the base and the exponent is a numeric value. In this case, it's the opposite. The base is a numeric value and the exponent is a variable. So we can't use the power rule. What we need to do is rewrite this function, rewrite this equation to resemble something that we do know. So there's a couple ways to actually approach this. Number one, we could write it as a logarithm. So if we write it as a logarithm, so if we rewrite this as a logarithm, it would be log base a of y equals x. So we're just rewriting that. Remember, it's log with whatever base you have of the exponent of the argument. The argument is what that is equal to the exponent. Log base a of y equals x. Well, what can I do with that? You might say, I don't know what to do with that because I don't know the derivative of log either. And you're right. But maybe we can rewrite this somehow. Maybe we can use the idea of the change of base to develop this. So the change of base formula for log says this. If I have a log with whatever base, let's say log base 7 of 10, right? I can rewrite that as log of 10 over log of 7, right? And when we do the change of base, it doesn't matter which base we put in here. The way I wrote it here, it has a base of 10, it's implied. But this is also equivalent to log base 3 of 10 over log base 3 of 7. As long as the bases are the same, we can rewrite it using the change of base formula. Now, that doesn't help us very much unless we have a log that we know. And so we can remember, maybe, that this would also be log base e of 10 over log base e of 7. And remember, we have a specific definition for log base e. We call that the natural log. So we could rewrite this as natural log of 10 over natural log of 7. So the idea is that we are rewriting our exponential functions or our logarithmic functions using natural log because we know the derivative of natural log. Well, why not use these? Because I don't know the derivative of those. So if I can get it down to natural log, we're good. So how could I rewrite this so that it is in terms of a natural log? Well, change of base would say the natural log of y over the natural log of a is equal to x. Okay? And then from here, we can actually take, well, I'm not going to do it yet, but we could take the derivative from here. It's going to get a little complicated if I do. Before I do that, I'm going to go ahead and multiply both sides by natural log of a. So I end up with natural log of y equals the natural log of a times x. Now, the reason I put the natural log of a out front is because I want to recognize it as something. A is a constant value. It's a number. We don't know what that number is, but it's a number. So when if I were to type this value, this value into my calculator and find the natural log of it, I would get a value out. I would get a number out. The point being that natural log of a is a constant, okay? And I'm going to parallel that with the example up here. If I rewrote this as a logarithm, it would be log base 3 of y equals x. And then if I rewrite that as change of base, that'd be natural log of y over natural log of 3 equals x. And then we'll multiply, so you get natural log of y equals natural log of 3, and then times x. Here you might be able to see it a little bit easier, right, because it's numbers. If I were to type in the natural log of 3 into my calculator, I would get a number out. So if I'm thinking about taking the derivative of that, well, what's the derivative of a constant? The derivative of a constant is 0, okay? Okay, I got to take a step back. That's if you were going to maybe apply the product rule. And that's fine if you do. I'll show two different ways of doing this. But we can also think of it as a constant multiple. A constant multiple. And what do we do with constant multiples? We take them out, we take the derivative of what's left over, and then we multiply them back in. Okay? So let's go ahead and take the derivative of this. What's the derivative of natural log of y? Well, that would be 1 over y. And then remember, we have to apply implicit differentiation, the chain rule, times y prime, because y is the function here, equal to, well, what's the derivative of this side? There's a couple ways of approaching it. Remember, this is a constant, so it's the same as saying, what's the derivative of 5x, right? Natural log of something times x, because that's a constant. The derivative of that would just be 5. So what's the derivative of this guy? That would be natural log of a, okay? Now, if you don't like that, that's fine. We can approach it through the product rule. If this is my first piece, what's the derivative of natural log of a? Well, that would be 0 because that's a constant, times the second piece, x, plus the derivative of the second thing, which is 1, times the first thing, which is natural log of a. And then you can see as a result, that just simplifies to natural log of a, and that's exactly what I got there, okay? Now from here, I would isolate y prime. So I'm going to multiply both sides by y, so I end up with y prime equals natural log of a times y. And this is where we might get a little tricky because this is the derivative, but we want it in respect to x, not in respect to y. So that's where we go back up to what was given up here, and we can replace the y value with a to the x. So we can say y prime is equal to the natural log of a times a to the x, because y is a to the x. And there we have our derivative. Okay? If I do the same thing over here, well, what's the derivative of natural log of y? I'm going to run out of room here, so I'm going to put it up here. The derivative of that would be 1 over y times y prime. And then the derivative of this side, because that's a constant multiple, would just be natural log of 3. We'll go ahead and multiply both sides by y. So we got y prime equals natural log of 3 times y. And then we need to replace that y with what it's equivalent to, which is in the original. So y prime equals the natural log of 3 times 3 to the x. And so maybe we can start seeing some patterns here. Okay? Now there's another way to develop the derivative of a to the x. We have y equals a to the x. How could I develop that derivative? Well, honestly, I forgot the other method, so let me get a little hint here from, I know I have two different methods here. Taking the natural log of both sides. Oh, okay, yeah. So this is pretty straightforward. So remember, whatever you do to one side, you have to do to the other. So if I take the natural log of both sides, I get natural log of y equals natural log of a to the x. Okay? Now, I can use my power rule when it comes to logs. Remember, when it comes to logs, we can take that exponent and move it to the front here, so we end up with natural log of y equals x times natural log of a, right? And from there, you can see that I have basically the same thing that I have right there. It's just a matter of getting to that point. So the derivative of this side is 1 over y times y prime. The derivative of this side, it's a little out of order. Normally we have our constant in front, and natural log of a is a constant, but the bottom line is the derivative is the natural log of a, and then multiply by y, and then replace the y value with what's given up there. So the natural log of a times a to the x. Okay, so that's a different approach to that derivative. And there might be multiple ways. There might be other ways that will get us to that, and that's okay if you have a different method. But the bottom line is we want to come up with a conclusive statement about exponential functions. So again, okay, so I kind of just did it backwards. That's the definition of logs here, getting the same thing. Okay, so that is that. But the bottom line is this. When I want to take the derivative of an exponential function, whatever that is, if I want the derivative of an exponential function, look at the result. The result is the natural log of a, in this case the natural log of the base, times the original function, a to the x. Let's go ahead and double check that over here. What's the derivative of 3 to the x? Well, it's natural log of 3, natural log of the base, times 3 to the x. It's exactly what it is, right? Now we can actually kind of test this with one that we know, okay? We can look at the idea of e to the x, y equals e to the x. Let's go ahead and look at this through the idea of natural log and just see what we come up with to make sure we understand what's going on here, okay? If I were to take the natural log of both sides, and I think I kind of developed this yesterday, move that x to the front, so we have natural log of y equals x times natural log of e. And just for our own sake, I'll rearrange this. So it'll say natural log of e times x. And then when I take the derivative, I get 1 over y times y prime equals, what's the derivative of this side? Well, that would be natural log of e, because that's a constant. We'll multiply by y on both sides. So we got natural log of e times y. And then we'll replace that. So we end up with natural log of e times e to the x. And that's exactly what we got here. What's the derivative of e to the x? It's natural log of the base times the function. The unique thing about exponential functions is, or about exponential functions with a base of e, is that the natural log of e is just 1. That's just 1. That doesn't simplify over here or over there, but it does simplify here. And that's why we came up with, well, the derivative of e to the x is just e to the x. Yes, it is, but it's actually multiplying by the natural log of e if you want to be consistent with all exponential functions. So again, the derivative of an exponential function is the natural log of the base times the original exponential function. Now you'll see in the lesson here, I replaced x with u, meaning that u is a function, so that we can apply this to we can apply the chain rule to this as well if we want to. The derivative of this is going to be the natural log of the base times the original function, and then times, if I'm going to apply the chain rule, this is a function up here, then it would be times u prime. Now right now that might seem like, well, what's going on there? Well, let me give you an example that we can work through and make sure we understand it before we go any further, okay? So let's say we have y equals 5 to the sine of x, right? If I want to take that derivative, I don't know exactly how to do that. Well, I can apply this rule, and I will. I'm going to do it right now, but then I'm also going to prove it the way we did before. Y prime here, y prime would be equal to the natural log of the base, so natural log of 5, times the exponential function, so times 5 to the sine of x. And then we have to apply the chain rule here, and we need to be able to see that. The sine of x is the inner function, so we multiply that by the derivative of the inside. So that would be times cosine of x. And so that would be my final answer for that function. Our goal is to be able to do it that quickly. The natural log of the base times the function times the derivative of the inner part of the function. But let's go ahead and prove it just to make sure that we understand what's going on here. Well, if I'm going to rewrite this, maybe I'll take the log of both sides. I'll take the natural log of both sides because I don't want to deal with log necessarily. I want to deal with natural log. And then I'm going to move that sine of x out front. So I've got natural log of y equals the sine of x times the natural log of 5. And then I'm going to move that natural log of 5 in the front because that's a constant. And then I'll go ahead and take the derivative. So I end up with 1 over y times y prime equals, well, that's a constant multiple, so it's natural log of 5, and then times the derivative of the function, so times cosine of x. And then we'll go ahead and multiply by y. So we end up with natural log of 5 times cosine of x times y, and then replace that y value with what it's equivalent to. So that would be the natural log of 5 times cosine of x times 5 to the sine of x. And that's exactly what we have here. The natural log of 5, 5 to the sine of x, and cosine of x. Again, our goal is to get to this point just straight off. But if you need more time to develop that, if you need to create it yourself, this is a good method. And in all reality, like I've said before, memorizing a process is fine, but what's more important is to understand where that process comes from. And this is kind of the explanation of that. So make sure you understand how to get it and how to do it quickly. Okay? So that is important. Let's go ahead and take a look at the next function, and that would be the log function, the general log function. Y equals log base a of x. And again, I'll parallel this over here where a is a constant, so I'll say log base 3 of x, just so we have a better understanding using actual numbers there, so we don't get so confused with the a. Well, we don't like this. We don't like this log base a because I don't know the derivative of log. So there's a couple ways to approach this. Okay, we could, as a first step, rewrite this as an exponential. So we could rewrite this as a to the y equals x, right? Just using the rules of logs, the definition of log. From here, I can actually take the derivative of this because this is an exponential function. Let me go ahead and rewrite this over here the same way. That would be 3 to the y equals x. Now, if I were to take the derivative of this, the derivative of 3 to the y, remember, is the natural log of the base times the function itself times the derivative of the inner function. Well, the derivative of y is y prime, and then the derivative of x is just 1. We're going to isolate y prime here, so we get y prime equals 1 over the natural log of 3 times 3 to the y. And there is our derivative for that. We can do the same thing here. We could say that this is the natural log of the base, so natural log of a, times a to the y, times y prime, because we're using the chain rule, equals 1, and then y prime equals 1 over the natural log of a times a to the y. Okay? And so there we have our log, the derivative of log. There's one more method to do this, and I find this second method actually probably a little bit more efficient in some ways. I'm going to use the change of base formula here and get it in terms of natural log. So I'm going to rewrite this as natural log of x over natural log of a. Now, if I want to take the derivative, I could use the quotient rule, and that's fine if we do. But just keep in mind that the natural log of a is a constant. It's a number. So the derivative of natural log of a is 0. Quotient rule, we'll do this real fast. That'd be y prime equals 1 over x times natural log of a minus, what's the derivative of natural log of a? It's 0 because that's a constant, times the natural log of x all over the natural log of a all squared. Then we can simplify that a little bit. That's all going to go away, and you're left with 1 over x times natural log of a over natural log of a squared. The natural log of a's can reduce, and so you're left with 1 over x all over natural log of a, but that can be rewritten as 1 over x times natural log of a, which is exactly, where's, oh, I forgot to replace this over here. I missed that step because remember we have to replace the y value. We don't want just y there. Now we don't want to say 3 to the log base 3 of x, so we would say y prime equals 1 over natural log of 3, and we know 3 to the y is given right here. 3 to the y is x. And so 1 over natural log of 3 times x. Same thing here. Y prime is going to be 1 over the natural log of a times, well, what's a to the y? It's x. And that actually cleans it up a little bit better here. Over here, what do we have? We have 1 over x natural log of a. 1 over x natural log of a. And so this is another way of doing it. I prefer working it out this way. And it's okay if you work it out that way, that's fine. But notice the general theme here, that if I want the derivative of a logarithmic function, whatever the base is, as long as it's a constant, and then I have a variable or even a function inside, the end result is that the derivative is 1 over the natural log of the base, natural log of a, times the argument, times the thing inside the logarithm. And so hopefully you can see that there's a relationship between exponential functions and logarithmic functions, okay? So let's go ahead and look at an example of this real fast using the chain rule again to make sure we're on the right track here. And I'm going to go ahead and write down that rule off to the side so I can use it quickly. If y equals the log with a base of a constant of a function, then the derivative of that is going to be 1 over the natural log of the base times the argument. And then we have to take all that and multiply it by u prime because u is a function in this case. So let's go ahead and take a quick look at an example here. And I'll use the sine of x example again. Y equals log base 3, or log base, how about log base 5, of sine of x. Well, if I'm going to apply that really fast, we notice that we have a composition of functions. The outer function is log base 5 of something, and the inner function is sine of x. So we have to apply the chain rule properly. But y prime is going to be 1 over the natural log of the base, so in this case the natural log of 5, times the argument, which is sine of x, put that in parentheses, and then we have, so that's the derivative of the outside thing. Now we need to multiply it by the derivative of the inside thing, which is cosine of x. And then we could simplify this a little bit if we wanted to. Cosine over sine is cotangent, so we could write this as cotangent of x over natural log of 5 if we wanted to. Now, let's go ahead and prove that. And again, being able to come up with that without just plugging it into the formula over there is more valuable. So if I have y equals log base 5 of sine of x, I'm going to rewrite this as a change of base. So y equals the natural log of sine of x over the natural log of 5. Now, one thing I didn't show in the previous, when I erased everything, is I showed you how to use the quotient rule here. And that's fine if you do. But there's a quicker way to do this because, again, natural log of 5 is a constant. I could rewrite this as 1 over natural log of 5 times the natural log of sine of x. And that's always my go-to. Okay, and I'll go over a quicker example of that in a second so you can see it. But the reason I could do that is because that's a constant here. So since that's a constant multiple, when I go to take this derivative, we're going to write it down, ignore it, right? And then take the derivative of this. Well, the derivative of natural log is 1 over the argument, 1 over sine of x, times the derivative of sine of x, which is cosine of x. And then you can see quite simply that that simplifies to that. Okay. Another quick example, just so we get good practice with this. Y equals log base 7 of x, really basic one. Rewrite it, so it would be the natural log of x over the natural log of 7. Rewrite that so that the natural log of 7 is out front, basically. And then that's a constant. So when I take the derivative, that hangs out. The natural log, or 1 over natural log of 7 is a constant. It's a numeric value, so ignore it. Multiply it by the derivative of natural log of x, which is 1 over x, and then multiply it back in. We could apply the chain rule, and it's always a good idea to keep the chain rule in the back of our heads. What is the inside of this function? Well, the inside is x. What's the derivative of x? It is 1. Okay, but that didn't change anything there. And so you can see that logarithms aren't a big, long process, but you have to know how to develop it, how to get it. Okay, so let's go ahead and take a look at what I did here to make sure we're all good there. So I took, in this case, I took the natural log of both sides, and then I moved the y down. I used that power rule thing. And then I took the derivative of both sides because natural log of a is a constant. And then I divided by natural log of a. And then, so I got 1 over natural log of a times x. Or I use the change of base formula here. And I pull that natural log of a out front like I did here. And then when I take the derivative, the natural log of a is a constant. So that gets taken out. And then the derivative of natural log of x is 1 over x. Careful, careful, careful. Again, I always get this issue. I talked about this in the last video. If I say natural log of 17 and I say, what's the derivative? Students are going to tell me 1 over 17. No, it's not. If you want to think of that as okay, natural log of something, okay, it's 1 over 17, but then you have to apply the chain rule, so times the derivative of 17, which is 0. So the answer is 0 there. The natural log of 17 is a number. It's a constant. So what's the derivative of a constant? It is 0. So be careful when you see natural log of some number and taking the derivative versus the natural log of x or the natural log of y. Okay? Now, what's the general rule there? We end up with natural log, y prime equals the natural log of the base, the natural log of the 1 over the natural log of the base times the argument. And then if you have a composition, then it's times the derivative of the argument afterwards. Okay? So that's an important one. Let's go ahead and write both of those down in general with exponential and logarithmic. So again, if f of x equals a to the x, then that would mean that f prime of x is equal to the natural log of the base times the function itself. Then if, we'll use g of x, is equal to log base a of x, then the derivative of that is 1 over the natural log of the base times the argument. Okay? So those are ones, again, you want to commit to memory, but know where they come from as well. Okay? So let's go ahead and take a look at some examples of where we might see these. So some practice problems. Maybe you could pause the video and see what you can come up with before you watch the rest of it. That might be a good idea. But we have y equals 2 to the t minus 3. And we are looking for when the tangent line has a slope of 21. So we know that the tangent line has a slope of 21. What does that mean? Well, that means that the derivative, the slope of the tangent line, the derivative is 21. So first thing we have to do is take the derivative. So y prime equals, this is exponential, so we'll use that rule over there. If we're not going to develop it, we would end up with the natural log of the base 2 times 2 to the t, right? We're taking the derivative of just this piece right now because this is an addition rule, sum and addition rule. And so we don't want to include that in our exponential. That's not part of the exponential thing. Now, what's the derivative of -3? The derivative of -3 is 0. And I've been seeing a lot of mistakes when it comes to taking derivatives with some sort of sum or difference on it. The derivative of a sum of a constant is 0, so we don't have to write that down. So there's our derivative. Well, what do we need to do with that? We need the slope to be 21. So what represents the slope? Is it time, or t, or is it y prime? Well, it's y prime. So we'd actually set y prime equal to 21, and then we would solve for t. So how do I solve for t? Well, the first step would be to divide by natural log of 2. So we have 21 over the natural log of 2 equals 2 to the t. And then how do we solve for t? Well, this is going back to rules of logarithms. We're going to have to rewrite this as a logarithm. So it'll be log base 2 of 21 over the natural log of 2 equals t. And then from there, we could type it into our calculator and get an answer out if we wanted to. I don't have my calculator present, so let's just see what I have here. So again, the derivative is going to be natural log of 2 times 2 to the t. And we would say 21 equals natural log of 2 times 2 to the t because we're isolating, or plugging 21 in. And then solving for that, 21 over the natural log of 2 is 30.297 with your calculator. And then we would take the log of both sides, so it would be log base 2 of that 30.297. And then depending on your calculator, the TI-89 doesn't have a nice clean button for logarithms to evaluate them. If you type in log, it's assuming a log base 10. So again, it might be a good idea to convert this to a change of base, a natural log. So it would be natural log of, well, let me rewrite this here. This is, we write, let's see, log base 2 of 30.297 equals t. So if I rewrite that using the change of base, that would be the natural log of 30.297 over the natural log of 2 equals t. That might be easier to type into your calculator than to try finding the log button that has a base other than 10. Okay, so just keep that in mind when you're doing that. And then as a final answer, we end up with t equals 4.921. All right, oh, and I guess I didn't answer the question here. It says, at what points on the graph does that function have a slope of a tangent line of 21? Well, we found the t value of 4.921. Now we need to find the y value because we're looking for the point, we're looking for the coordinate, the x comma y, or in this case the t comma y. So we're going to go ahead and plug 4.921 back into the original equation to figure out the y value there. And again, this is all calculator work. And so you end up with 27.297, which means your coordinate is going to be 4.921 comma 27.297. Okay, so that's an example of where you might see exponential functions taking the derivatives of those. Let's go ahead and take a look at a different practice problem now. Again, now we're dealing with logs. And there's a couple ways of doing this. So go ahead and give it a try before you watch this. So for this problem, we got y equals log base 3 of 3 raised to the sine of x. Okay. Now we can go through the big, long process here of trying to prove what the derivative is, and that's fine if we do, but I'm just going to try and shortcut it here. Okay. So y prime is equal to, this is a log function with an inner function of sine of x, so it's going to be 1 over the natural log of the base, so natural log of 3, times the arguments, so times what's inside the log, so times 3 to the sine of x, and then times the derivative of the argument, so the derivative of sine of x is cosine of x. All right? So that's what we have there. Oh, yeah, that's right. Okay. And then we can try and simplify this. This is really not looking very nice, to be honest with you. Something seems out of place. Did I do something wrong? Well, log base 3 of 3 to the sine of x, where this is the inner thing, that's the argument. Oh, I know what I did wrong. Here we go. So instead of multiplying by cosine of x, I screwed up my chain rule here. The inner function is 3 to the sine of x. Okay, so where x is my inner function here, 3 to the sine of x is my inner function there. So I have to multiply it by the derivative of that inner function. So there's an exponential function. What's the derivative of 3 to the sine of x? Well, it's the natural log of the base, so natural log of 3, times the 3 to the sine of x. And now the inner function is sine of x, so we'd have to multiply that by cosine of x. Now that looks really disgusting, but what you notice is that all of these, the natural log of 3 and the natural log of 3, cancel out. The 3 to the sine of x and the 3 to the sine of x cancel out. What are we left with? We're left with just cosine of x. So that begs the question. That forces us to think, could I have done it easier? Could I have done it in a simpler way? And hopefully you saw it. Hopefully you saw it. If I have y equals log base 3 of 3 to the sine of x, I can apply the power rule here and move that sine of x out front. So we got y equals sine of x times log base 3 of 3. And then from there, we should recognize that the log base 3 of 3, well, 3 raised to what power is 3? That's just 1. So this function is actually sine of x times 1. And therefore sine of x. What's the derivative of sine of x? It's just cosine of x, or y prime is cosine of x. So that's that. Okay. All right, that's that. I'm going to tell you right off the bat, there's not a lot, I don't have a lot of practice in here for logarithms and exponential functions. Students tend to get kind of stuck on these types of functions because there's a lot more to them. Again, know where to develop it, know how to develop it, and then know the little shortcut here, but find a way to get practice. Get on Delta Math, get on Khan Academy, get in a book, and get these practice problems done so that you can understand what's going on, okay? And that's basically what we have there. All right, So with that said, that wraps up every function that we can think of in terms of taking the derivatives. We started off with really basic functions, like functions you learned in middle school, constant function, linear function, right? We talked about sums and differences. Then we got into the power rule, so we could deal with quadratics and polynomials. We got into radical functions, which still dealt with the power rule. Then we got into the product rule and the quotient rule and all those things. So let's go ahead and summarize all of that. The first one is the constant rule. Well, what's the constant rule say? I probably should write all this down to make sure that everybody's on the right path here. The constant rule. The constant rule is basically that the derivative of any constant, the derivative of a constant is 0, right? So if I have a horizontal line, thinking of it graphically, the derivative of a horizontal line is 0 everywhere, okay? Then we have the constant multiple rule, and so if we have the derivative of some constant times a function or times some variable, that derivative is c, okay? Because we basically take the constant out, find the derivative of x, and then multiply it by the constant. Maybe I should do this. Maybe I should write it as cu, where c is a constant and u is a function. Then we would take the constant out and find the derivative of the function. Now if I simplify that, that becomes a constant times u prime, because u is a function in respect to x. Okay? The next rule was the sum and difference rule. So that said, if I have the derivative of some function plus or minus some other function, well then I can take the derivative of each of those, or essentially, I'll write it like this. That would be u prime plus or minus v prime. So that's the sum and difference rule. Then we got into the power rule. The power rule stated that the derivative of any base of anything, let's say it was x, right, raised to a constant, the derivative of a variable raised to a constant is equal to multiplying the constant to the front, multiplying the exponent to the front, and then subtracting 1 from the exponent. So that's the derivative of a power. We have the product rule. Now the product rule will look similar to this in its setup, but the result is completely different. If I have a product, it's not going to be the derivative of u times the derivative of v. It's going to be the derivative of the first thing times the second thing plus the derivative of the second thing times the first thing. So that's the product rule. Then we have the quotient rule. The quotient rule is if you have u over v, where these are both functions, that's u prime times v minus v prime times u all over v squared. We have the quotient rule. Then we have the chain rule. So if we have a function inside of a function, so if I'm taking the derivative of, how do I want to write this? If I'm taking the derivative of f of g of x, that would be f prime of g of x, because that's the derivative of the outer thing, and then times the derivative of the inner thing, which is g prime of x. So that's the chain rule, and there's different ways to represent that. We have implicit differentiation. Implicit differentiation is if we have a function that is in respect to x, but we have a bunch of other, where the y value, the function, is not necessarily isolated. So the bottom line for the implicit differentiation is that the derivative in respect to x of y, we say is y prime, right? So we have to apply the chain rule there, where we have something like 7y to the fourth, where y is a function. The derivative of that in respect to x is going to be 28y to the third using the power rule, and then times y prime. Okay, so that's kind of the implicit differentiation. Then we have the inverse functions. So this one gets interesting. If I have an inverse function, let's say I have f of x is equal to the inverse of g, and I want to find the derivative of f. Well, I can't directly find the derivative of f. It gets pretty ugly. So what do? Because I want to get rid of the inverse, I take the g of both sides. So I got g of f of x equals x. and then I take that derivative, so that would be g prime of f of x times f prime of x, and then equals the derivative of x is 1. Then we can isolate f prime of x, and we get 1 over g prime of f of x. And so you can see how that's kind of related to our implicit differentiation, because we have a function inside of a function, right, in our chain rule as well. Okay, so that's inverse functions. And then we talked about the trig functions, right? The derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared, the derivative of cotangent is negative cosecant squared, the derivative of secant is secant tangent, and the derivative of cosecant is negative cosecant cotangent. Those are all things that you should know. And then, of course, the inverse trig functions, and that was dealing with, just trying to give a nice summary of all of these, that if I had an inverse function, let's say arc sine of x, well, I had to get rid of that inverse, kind of like what I did over here. So I would take the sine of both sides, and then take the derivative, so we get cosine of y times y prime equals 1. Isolating y prime, we get 1 over cosine of y, but then we had to develop that triangle because we need to replace y with something. So then sine of y, that'd be y for the angle, and then x, 1 there. So our Pythagorean theorem gives us 1 minus x squared and the square root of that. And then cosine of y is adjacent over hypotenuse, so our final answer is 1 over radical 1 minus x squared. I know I kind of flew through that, but that's something that we've talked about already. And then what else do we have? We have the derivative of e to the u, which remember is just e to the u times u prime. And then a to the u, that's what we dealt with today, the exponential function. The derivative of the exponential function is the natural log of the base times the function itself, so natural log of a times a to the u, and then you could say times u prime. And then we have the derivative of natural log of u, which is 1 over u, and then times u prime, because if we're going to apply the chain rule. And then the derivative of a log function. So the derivative of a log function was 1 over the natural log of the base, so 1 over natural log of a, and then times the argument, so times u, and then times u prime outside of all of that. So that wraps up all the derivatives of all the different functions that we have learned from middle school all the way through high school, dealing in Algebra 1, Algebra 2, or Math 1, Math 2, Math 3, depending on how you learned it. But that's a quick summary of all of it. If you have any questions on any of these in particular, please reach out to me by commenting below or finding me in a tutoring session. Otherwise, I will talk to you all later.